Hey guys, Matt Hoots here with Rated Green, and you guys have been along for a long journey with us as we're looking at the 1920s makeover ATL. All of this started when we were talking to Chris with LG Squared. He did this webinar with ROCKWOOL, and we also explored how we do all of this insulation below the slab, on the walls, how we're building this from the ground up. So what I want to talk about today is the perfect wall. Now, what is a perfect wall? It's basically an advanced way of insulating, air sealing, keeping water out, keeping water vapor out in a logical manner. So let's first look at how Chris with LG Squared first introduced the perfect wall concept at a ROCKWOOL webinar.
So taking these principles, we started to come up with our own idea of what a perfect wall meant. This concept of a perfect wall, we've heard it from what some people call him the father of building science, Joe Stiebrick with Building Science Corporation. It wasn't his term. He uses it a lot. He teaches it a lot. But it has been around for a long time. And so what we're trying to do as designers, which is what we do when we're, as architects, we're designing these buildings. We're designing the building science as well. So it's not just the aesthetics of the home and the functionality and it's designing the assembly so that it works, so that it lasts. And, just like we have to understand scale and proportion as an architect, when we're designing assemblies, we need to understand hygrothermics, thermodynamics, and these principles are just as important. So I mentioned control layers, and in the upper left there, you see we have 4 primary control layers, and that's water, and then, water, air, vapor, and heat. Those are the 4 main control layers, and you put them, and you see in this assembly, everything is to the outside of the structure, and this is our preferred way of designing and building, because again, for continuity of our insulation, there's absolutely, in all the homes I'm going to show you, we have absolutely no insulation in the cavity except for one project. And so everything is to the outside. It becomes, and we're finding now that the installation of exterior insulation is actually less labor than trying to get the cavity insulation installed correctly. And if you know about correct installation of bats, it takes a lot of work to get it right. You're cutting around wires and boxes and making sure that it's flush with the studs. You don't have depression, and you don't, every time you depress the insulation, compress it, and you have more than 5% compression, then you're starting to lose the R value. And there's published data showing how much the R value changes as you compress the insulation, every a certain amount. So with it all to the exterior, you don't have that, you're not losing, it's straight. This is all rigid insulation that we're using here. And labor, it's just like stacking bricks. You've got either 2x4, 4x4, or 4x8 sheets, and they just stack up, and it goes up so quickly sometimes, and especially on the roof where you're just almost walking on depending on the pitch, you're just walking on a floor there, and you just run it along. And it just becomes anyway. So that's something we'll show, but that we're learning that install of exterior versus cavity is simpler in our experience. So these are things we look at too. When dealing with this exterior insulation, you see here is a comparison of 2 layers of exterior versus everything in the cavity. And what we're looking at on these diagrams is what is our sheathing temperature. And sheathing temperature matters because if it is cold, if the sheathing is cold, this is where the condensation can happen. And this is what we look at when we're looking at, I'll talk about this here. This is a hygrothermic analysis, and it shows us where our risk level is for moisture. So when we get to this, when we have a sheeting temperature close to the inside, we're less at risk of having any condensation buildup, because we're not reaching dew point here. Whereas if we have a wall with cavity insulation, our temperature here, this is in Western North Carolina, showing a sheeting temperature of 18 degrees. And if you reach dew point, you're going to have condensation on the sheeting. It depends on where, it just depends in this cavity on where that condensation happens as to how damaging it can be. You know, your sheeting can, if it stays saturated for too long, it can start to corrode. So this analysis here, this is from one of our building science friends here at ROCKWOOL. Actually, he does these, will do these for us. And so what it shows is this here, this green line is our threshold. We don't want our moisture risk to reach this level. And so you see, these are the different assemblies that we had on a particular project, and we were just sampling each one. This, the one that has the least risk, the further away from this green line, that's the right balance of insulation on the exterior. Nothing, and these, same thing here. We were just looking at different options for the amount of insulation. So this is the exterior side of the sheeting layer, what the RH is, and that's this spot right here. And then the water content in the sheeting layer, the moisture percentage, that's what this is here, and it's showing us that we're well below our threshold. So this is our risk line, and we want to stay. And this, by the way, as you can see, this is over an entire, from 2016 to 2019, showing worst case scenario for 3 years. So each one of these peaks is a bit, it's the same time of year here. So this is just showing the worst case scenario on the home in a certain assembly, and showing that we are well within our well below our risk level. So this perfect wall, as I mentioned, it can be done anywhere in the world. These projects we've done, and what changes is the amount of insulation. Everything else stays the same. We put all of our air and vapor control layers right on the exterior side of the sheeting. I can go back to this right here. This is where our air and vapor control layers are. And then we put our thermal control layer out here. And then our bulk water control layer is the cladding. And so we want to make sure that is solid and robust, so we don't get any bulk water into this assembly. But as I said, especially with the right insulation, with a drained, vented cavity, which is a rain screen, we can allow water to get in there because it dries. So this is the idea of a perfect wall, and this is what we have designed as our perfect wall that continues to work today. So again, anywhere in the world, this assembly, the control layers to the exterior, the way we've got it, can work anywhere.
Everything underneath this slab had to go together in a certain order for it to work perfectly and be part of our perfect wall assembly. Let's take a look at the basement. Let's look at the demolition phase. We took out everything that was in place. We took out the framing, we took out the foundation wall, and we completely rebuilt the foundation wall on 3 sides. Now on the front wall, we decided to leave it. We decided to do shotcrete there because if we took that out, the house would have fallen down. Plus we had a front porch, so we wanted to keep in place. We basically got it down to the dirt, Georgia red clay, made sure everything was compact, got all the debris out. We had 3 or 4 different layers. Now we decided to make the basement all one level. Now we still have a ledge, so we need to leave this ledge in place, mostly for structural reasons. But for the most part, the basement is flat and level now. So starting with the dirt, made sure everything was level compacted, had an engineer come out, and he also tested all the footings to make sure that we have good compaction in the footings, and also that when he did a probe test, and he also did a torque test, which I haven't seen them do before, we made sure that we had the right PSI in the footing, so there's not going to be any issues in the future, cracking foundations or anything like that. So once we got all the dirt out of the way, the next layer that we had to worry about was putting down a geotech mat. Now the reason we put this down is because typically you can put gravel down and you pour a slab on top of that and you have a vapor barrier. Because we have so many different control layers, so we didn't want them to mix with each other, we put the geotech mat down first, then we put the gravel. Now the gravel was in place mostly for the radon system. The radon system needed something to breathe, and the gravel with the geotech mat preventing the dirt from entering into the gravel layer. You've got basically gravel, which is structural, and it also breathes. You have air in between the gravel. So what this allows the vents and the radon to do is we've got a passive system. These vents are going to be able to take any gases, moisture and whatnot from the gravel layer into the vents and out through the roof. Now this is the passive system. I've got a picture of the pipe in there, and the difference between an active and a passive system is this is designed to not have to have a fan. Now if we do test and we do have radon in the future, we can add a fan if necessary. However, this fan is designed just to use nature, Bernoulli's principle, which is basically if wind blows across the house, it creates a negative pressure underneath the slab because this pipe is going to go all the way through the roof. So we talked about the dirt layer, geotech mat, then we have the gravel. Now on top of the gravel, we're going to put the insulation. So a lot of people get confused about this. They usually think the vapor layer, then they have the thermal control layer. Well, we put the ROCKWOOL insulation, and this is Comfort Board 80. We use the Comfort Board 110 below the slab because it has a higher compression rate. And we put 4 inches of insulation all throughout the slab, except where we had the grade beams. And I'm going to talk about that in a separate video, how we can design, in the future, a better slab where you don't have to worry about grade beams in there. But for now, let's talk about the ROCKWOOL insulation. The reason you want this below the slab is because if you're creating a passive house, you want insulation on all 6 sides. Now, typically you insulate the walls, usually inside the walls. You insulate maybe the ceiling or the roof line. However, this is going on the outside of the structure. So below the slab, on the outside of the foundation walls, on outside of the framing, and on top of the roof. But first, we need to make sure that we put the insulation below the slab. If we don't do that, then the other insulation, you can have that heat gain or that heat loss, depending on what time of the year it is, through the slab into the ground. Now with this, the ground is typically around, let's just say 58 to 60 degrees, depending on what climate zone you're in. That is pretty cold to the touch. Now, if you're walking across this slab with this ROCKWOOL in place, it's going to be room temperature, which is much nicer to the feet and also helps with their energy bills. Now, on top of the ROCKWOOL, we have our vapor control layer. Now, the vapor control layer, we use Stego Home for this one. Stego Home is a 15 mil plastic made by Stego, and it's their Stego Home product. It's that green product that you saw with the red tape, kind of looks like the holidays. Now with this, we made sure it was fastened to the foundations, fastened to the footings. We also wrapped it up the wall behind me. So before we put the shotcrete in place, we put the Stego Home all the way up to the very top. That way, if any moisture comes from the outside, it's going to hit that. It's going to hit our gravel layer below. It's continuous. We've got a continuous sheet from the front to the back with the seams. Now we use many different things to mend the seams. We used a double stick tape, the double tack tape that they have, the Stego tack tape, and we also used the red tape to tape over the seams. Now along the foundation or wherever we're hitting an uneven surface, we use some of their mastic. So all the way around the side, we use their mastic and we use the tape. So in each joint, we have at least mastic plus tape, or we have the double tack tape plus the regular Stego Home tape to make sure that we've got a complete barrier all the way around. Now, on top of this, we made sure that this was sealed all the way around. I personally went through and made sure there's no penetrations. Like when the rebar was put in, they made a couple holes in the front wall. So I came out one evening and made sure all that was tightened up. So we've got a complete vapor barrier from the front of the house to the back of the house. Now what this is going to do is not only does it take care of the vapor, but also takes care of the radon. So these radon control layers, so radon, if you have the vapor control layer, what this allows it to do with concrete on top, and I was told radon is best with the radon control is best with the concrete on top. Basically, it's going to bounce around. It's not going to have any air leakage into the house through the slab, any moisture leakage, or any of the soil gases that are coming through into the house, because we've got a complete seal all the way around. And it's going to find its way through the gravel, basically the air in the gravel, to the radon pipes and go through the roof. So anything that is collecting behind me, which is the
the front of the house, or anything that's below the slab is going to hit those control layers, go through the pipes, and go through the roof. Now, finally, on top of that, we've got our, we had spec'd for 4 inches of concrete. I think we ended up pouring about 6 inches of concrete. And I think we had spec'd for 10 inches of shotcrete behind me. I think we ended up doing 12 to 14 just to make it a little bit stronger. So we've a little bit over-engineered this house, but we don't want to take any precautions.
So now that the basement is completed, we have to look at the continuity, how we take it up the walls and at the roof.
One of the things we talked about is like different control layers. So with the zip system, we've got our water resistant barrier. We also have our air control layer. So those are the 2 control layers. Now the next control layer that we have is the thermal control layer. So we've got 8 inches of ROCKWOOL insulation. Now this ROCKWOOL is R4 per inch. So 4 times 8 is 32. R32 just between the zip system and the edge of the ROCKWOOL. Now once you add the zip system and some of the things on the inside, you're going to add a couple R value, but for the most part, the effective R value of this is R32. The reason I said effective R value, when you're dealing with this type of construction versus normal construction where you're doing stick framing, you're packing the insulation in between the studs, the stud is about R1 per inch. The insulation could be R16 or actually it's going to be R14 because it's 3.5 inches in that stud base. So every 16 inch on center, you're going to have R4 versus R14 in that particular area. So what we've done with this insulation, we're wrapping the whole house. If you're wondering what this jail cell is right here, this is where a window is going to go in place. So once the window goes in, we're going to pack it with insulation around it and trim it out. So this is called continuous insulation. This is part of the perfect wall system. So the perfect wall has all the control layers on the outside of the house. You've got your water control layer, you've got your air control layer, which is all within the zip system. You have your thermal control layer, which is the ROCKWOOL. And the last but not least, on top, we've got these furring strips right here. These furring strips are in place and they're serving a dual function. They're not only holding up the ROCKWOOL insulation, because we have these screws going all the way through these pilot holes that we drilled into the studs. It holds the ROCKWOOL insulation up, but the furring strips also allows us to add the cladding. In this case, we're adding fiber cement. We're also adding AZEK trim on the outside. So anywhere where you have to put a nail through, because the nail is not going to go through all 8 inches of the insulation, we have these furring strips. Now on the corners here, you can imagine that if we tried to put a furring strip right here and this is going through the corner, the challenge is from here to here, this is 8 inches of insulation. On this side, we don't have any solid mass to go into. So what we're gonna do in the corners is we're actually gonna build out, have like a wider corner board. And what that's gonna do for us as well is going to kind of pull this tight. It's gonna pull it together. That way we don't have any gaps in the insulation. Now we did do an insulation inspection. We found a few gaps. So what we're gonna have to do is either pack that full of more insulation, because we want a continuous amount of insulation, no air gaps, continuous ROCKWOOL insulation all the way around. Otherwise, the effective R value is not there. So the next thing I want to talk to you about is how we install this particular ROCKWOOL. Now I'm doing a layout right here, and what we have is you want all of the horizontal and the vertical seams to offset a little bit. And the reason is as water comes down, if it happens to make it through the cladding, which is your first primary defense of the house to keep all the bulk water off the house, if it happens to make it through that and hits any of this insulation, if you overlap the gaps, that kind of acts as a self-flashing. You don't have to worry about water getting through that to the other control layers, and also it keeps the building dry. The other good thing about using ROCKWOOL insulation, we're very close proximity to some of the other houses around here. It acts as a very good sound control layer. That way you don't have to worry about sound if someone else is having a party, or if Piedmont Park is next door and if they're having a concert, you don't have to worry about all the different noise. It also, ROCKWOOL is very good for fire resistance. It doesn't burn, and this is made out of basalt, which comes from volcanoes, and steel slag, both things that has a very, very high flash point for burning, and it doesn't melt. So we've got demonstrations where we've taken an actual torch to it, and you can take a torch to this. It's gonna basically just gonna laugh at the heat. It's not gonna go through the heat. It's not gonna go through the insulation. It's not gonna burn. So if the neighbor's house catches fire, we don't have to worry about this house, because it basically has a fire blanket all the way around it. has a thermal blanket all the way around it, has a sound blanket all the way around it. So you can see that just with this one product, we've got lots of benefits just from this one product. So we only have the furring strips above grade where we are going to attach the siding and also the cornice and all that. Everything below grade is going to be stucco. ROCKWOOL does have an application where you can apply stucco directly to it. We're probably going to use something, we're going to have some other control layers that gives a little bit of air gap there. That way things can dry out before it gets to the ROCKWOOL, and also it holds the stucco in place. Now this is how we're doing the wall assembly. Here's a quick diagram of what the roof is going to look like. We're going to have outriggers, and we're going to have, instead of the two layers of the 4-inch ROCKWOOL insulation, we're going to have 2 layers of 5-inch. So we're going to rip down some 2x6s. That way we have 5 inches. We're going to create these little structural outriggers. That way we can create a little bit of an overhang effect on this, get a little bit of protection from the sun, so we don't have all the solar glare into the house. And you got 2 layers of the 5-inch insulation. So R40 with that, and we're going to stick ROCKWOOL bat insulation on the underside. All these control layers, the air tightness, keeping the water out, and all this insulation plus the R factor and the U factor of the windows is what we have to do to make this a passive house. Now, one of the other questions that I've got with this is like, what are you using to attach it? This is a screw that basically has the threads just on this side. So this is a 12-inch screw. You've got basically this part right here. There's no threads on the first 8 inches. This is going to attach. It's going to go through the plywood into the stud. Now you want to make sure that you're finding the studs with this. If you're just going through the plywood, it's going to fall out. That's not enough leverage, but this is very strong. If you were installing these every 12 inches, the furring strips are going to be strong enough to be able to help the cladding, the siding, whatever you put onto the structure. So this is the secret sauce right here. Now, this one right here is a galvanized screw. You can also use stainless steel. Unfortunately, I had a really hard time sourcing screws that were 14 inches or 12 inches long. Now, we're still able to use a galvanized screw with the modeling that we presented to FIAS and make sure that we are going to pass the overall energy analysis that we're doing.
All right, we're going to let Chris at LG Squared quickly summarize how all these different systems go together. The perfect wall below the slab, the perfect wall on the actual walls, the perfect wall on the roof. He's going to talk about how continuity is key and how all these systems go together.
So continuity, without taking this perfect wall and continuing it to the roof and to the floor, you start to have, you can risk having a failure in that enclosure. So if you, as you're building up these layers, everywhere that there's a potential for a break in that layer, you have to address it and make sure that everything stays continuous. Here we are with those control layers shown, and this is just a schematic of what I'm talking about: the wall, the roof, and the floor, all being continuous and wrapping the entire structure like an igloo, like a cooler. You have this is our perfect assembly. This diagram on to the right here is from a project that we are finishing up building right now here in Atlanta. That we've got 7 inches of stone wool on the roof and 4 inches on the exterior on the walls, and you can see it's just absolutely continuous. We've created overhangs to the outside of the structure, so we've attached them to the sheathing and they cantilever out, and we just ran the insulation out here, and that helps us with keep our temperature the temperature of our framing regulated as well, because without the insulation wrapping the outriggers, they will expand and contract differently than our fiber cement, and then we start getting gaps and cracks where we don't want them. So that's why we decide to continue this overhang to the exterior. And we'll show another project later where we didn't have any overhangs, and it just became this sort of this principle here, the continuity, form followed function. So the function is keeping the insulation continuous, and then the form of the building was informed by this function.
Thanks again for joining us on this journey as we continue to explore better building products and practices to help you have a more durable, healthy, safe, comfortable, and energy efficient home. For your convenience, we've uploaded other videos just like this. If you enjoyed this video, we appreciate it if you hit the like button and also hit subscribe and leave a comment below if you have any other questions about this topic.